Hey guys, welcome to Putnam Recitation. Well, it's a new year and we haven't seen each other for a while, but I would like to continue with the Putnam, even though the semester is kind of over, but I decided to go further with the winter session. And in fact, we have not many lectures left to finish off the entire course. And since the Putnam is on February 21st, I decided to go further. So let's start with the recitations, with the second part of the recitation. The first part was delivered by Jack. He talked about some problems, from some old Putnam problems. And I'd like to talk about some other Putnam problems as well. And the first problem that I have in mind is the following. So problem one, let's say, this was a Putnam A2 in 2010, so in 2010. And the problem, it's a pretty easy problem, but anyway, let me state it. It says that it asks us to find all differentiable functions, so find all differentiable functions f defined on R and real valued such that we have the following condition, equality, whatever you want to call it, f prime of x, so the derivative of f is nothing else than just f of x plus n minus f of x. Everything over n, right? For all real x, real numbers x, and all positive integers n. All right. Well, when you see this kind of problem, well, this is nothing else than just a functional equation. As you can see, you kind of have the difference quotient there. So you would expect that maybe the derivative to be constant or something like this, right? Anyway, we're gonna, and when you have a functional equation of this type, it's better just to see what happens, which holds for all real x and for all positive integers, and it's good in a way to see what happens when, for example, when you plug in x equals some particular real number. And in our case, let's see what happens for x equals 0. So for x equals 0, we have the following. So let's see, what do we have? So we have f prime of 0 is nothing else than just f of n minus f of 0 over n, right? Or if you want, this will imply that f of n is nothing else than just f of 0 plus n times f prime of 0. Well, if you look at this, and maybe you can recognize this in a certain, in some sense, this equality here, if you look at it, it's kind of looks like the equation of a line, right? In slope intercept form, right? So this implies that. So this means that. This means what? This means that f of n is how should I say? F of n is situated on the line of slope f prime of 0. Right? This is the equation of a line in slope intercept form. Well, of slope f prime of 0 and intercept f of 0. So that's what we have to know. All right. That's great. And now let's look at f. Let's see if we, instead of x, we have, we plug in x, x plus 1, what happens? So now we have that f prime of x plus 1 is f of x plus n plus 1 minus f of x minus f of x plus 1. Okay, let me write it in this way, minus f of x. Right? All right, everything over n. Sorry, here made a mistake. Here it's, yeah, no, it's correct. Okay. All right, so we have this. All right, great. But now if we look again, right, we know that f of, we can write this further on, and this would be nothing else than just n plus 1 times f prime of x, everything over n, right? Times f prime of x over n. So this will be equal to nothing else than just, let's see, sorry, minus here. So this would be nothing else than just f prime of x. So this implies that what? That f prime is periodic of period 1. F prime is periodic of period 1. Right? Because we have, if you look here, we have f prime of x plus 1 is nothing else than just f prime of x. So that's what it means for a function to be periodic with period 1. All right, great. All right, at this point, everything becomes clear because I can write in the following way. So thus, if I can write it in this way, the integral from, let's say, t to t plus 1 of f prime of x dx will be nothing else than just the integral from 0 to 1 of f prime of x dx. And also, we know that f of x plus n minus f of x is nothing else than just the integral, this would be n times the integral from 0 to 1 of f prime of u du. Anyway, this is clear using the fact that this is periodic, and we also use the fundamental theorem of calculus. So this guy, if you look at this guy, this integral, right, is free of x. And this integral here is free of x, which is great. So this implies that, so this means that f prime of x, because this guy, look at this guy here, f of x plus n minus f of x, right? If you go back to our, you see f of x plus n minus f of x, everything over n is f prime of x. So this would be, this implies that f prime of x is constant, right? So f of x is, or all affine functions, right, with a, b real numbers. And these are the functions that we're looking for, right? It was pretty straightforward. It's just like a typical functional equation, and the only thing you need to observe was the fact that this guy equals this guy. So basically that f, the derivative f prime is periodic of period 1. And then you can write this in this way, that the integral from the, you can write it in this way here, that the integral from t to t plus 1 is the integral from 0 to 1 of f prime of x dx. All right, that's beautiful. That was a Putnam A2 anyway. If you ask me, I would say it's a pretty standard, as long as you know what you're doing. So, all right, now the second problem that I have in mind and I would like to discuss is the following. And again, this was a Putnam, I think, Putnam A4 in 1973, so a long time ago. But it's a very nice problem, and I think I've discussed this. The idea, I've discussed it before in another lecture. Anyway, you will see exactly, I'm not going to divulge the idea right now. Well, let's write the statement first. So the problem says the following. So it's more like a question. How many zeros does the function f of x equals 2 to the x minus 1 minus x squared? Pay attention now, because we have x squared half on the real line. Right? So this is the question. And we would like to see what happens to this function. Well, if you look at it, you have this, you sort of have a combination between an exponential function and a quadratic function. Well, at some point, the exponential function will grow fast enough, so there is no way that the quadratic function will catch the exponential function. All right. So probably, as you can guess, you would be tempted to say that there aren't so many solutions for the equation f of x equals 0. Or in other words, there aren't so many, there are not many zeros for this function. Well, let's do a case study first. Let's see what happens if x is negative. Well, if x is negative, we want to take this, to eliminate this possibility right away. F doesn't have any zeros. And why is that? Well, it's quite clear that because, well, let me write it. Let me give you an argument. Right? Because for example, 2 to the x will be less than 1, and 1 plus x squared will be greater than 1. So there is no way this guy will be 0, right? So, all right, that's great. Okay. Wait, what's... Okay. Wait a second. All right. So as you can see, so just like we said, if x is negative, the function does not have any zeros. All right. Now let's see what happens if, let's see if we see some other zeros. Well, if you look at the equation, so the equation, let's say, f of x equals 0, has solutions, let's say, let's see, x equals 0. Does it have x equals 0? Well, sure it does. 0, let's say what other? 1, all right, great. And maybe others. Maybe some others. We have to check on this. But at this point, we know for sure that there are 2 of them, 0 and 1. So we have at least 2 solutions at this point. We know that for sure. So what we know is that for x negative, we don't have any solutions. We know that for x equals 0 and x equals 1, we have solutions to our equation. And now let's see if we have some other solutions. Now, from, so we have seen 0 and 1. What about if we look at f of 4? So, now let's look at f of 4. So f of 4 is 2 to the 4th minus 1 minus 4 squared. And this guy is 16 minus 1 minus 16. So this is negative 1, which is negative, right? It's less than 0. And f of 5, so if we look at this guy, f of 5 is what? So it's 2 to the 5th minus 1 minus 5 squared. So this is 32 minus 1 minus 25. Definitely this will be positive. So this is 6, which is positive. And we know that, and moreover, f of x, let's write it explicitly. Okay, in fact, we know. Anyway, let's write it again. Is a continuous function. That's obvious, right? It's just a linear combination of continuous function. So by the, since it's a continuous function that goes from negative to positive, it has to go through 0. So by the intermediate value property, right, remember from the continuity? So by the intermediate value property, there exists a number, let's say x naught between 4 and 5, such that f of x naught is 0. So at this point, we have 3 solutions. So at this point, f has at least 3 solutions, 3 zeros, let's say. Okay, so f has at least 3 zeros. Well, the question is, do we have other zeros as well? So that's the big question. Well, are there any other zeros? That is the big question we would like to answer. Well, maybe there is some, but probably as you might expect, but maybe not. And now let's see. So we have this function. So the short answer is probably not. And we compute the derivatives. So, and you will see why we will do this. Because I would like to apply a certain technique that I showed you in one of the lectures. And the first derivative, f prime of x, is 2 to the x log 2 minus 2x. And the second derivative, if we want to differentiate this one more time, is 2 to the x log squared of 2 minus 2. Well, we will show that there are no other zeros. So we show that f does not have any other zeros. All right. So let's see. So suppose that, so if f has another zero, so if f has another zero, right, then, well, since we know that f has 3 zeros, then f has at least 4 zeros. All right, and here comes the trick. So here so it has 4 zeros. So f has 4 zeros. So by applying Rolle's theorem, so you remember we did that in the Putnam B1 2016 when we talked about it, and we said that between any two zeros of the function there is a zero of the derivative, and so on, and we keep going with this. We call this the Rolle sequence. But anyway, by applying Rolle's theorem, it follows that f prime has at least 3 zeros. Then f second prime has at least 2 zeros. And finally, then ultimately, the third derivative, f third prime, has at least 1 zero. Right? By just an application of Rolle's theorem. But now let's see who the third derivative of f is. But f third prime of x is nothing else, so we'll differentiate that one more time, is 2 to the x log cube of 2, and that's it. But this is different than 0 for all x. So that's contradiction. Well, where did the contradiction come from? Well, it came from the fact that I assumed that f has another 0, which does not. So, okay, so we can say as a conclusion that finally f has 3 zeros. And that's it. That's a very nice problem, right? Anyway, so when you have these kind of problems with how many zeros, you always think of certain type of mean value theorems, or Rolle's theorem, or Fermat's theorem. Anyway, now let's veer towards something else. So problem number 3. Again, this was a Putnam B1, and I saw this also in this, so Putnam B1 in 1980. But moreover, I saw this a couple of times given at the in the Berkeley preliminary examinations book, right? Which collects all these problems given at the Berkeley preliminary exam for PhD students. Before you become a candidate for a PhD, a doctoral candidate, you must pass this what we call qualifying or preliminary exams. And at Berkeley, there is this book which is called exactly like this, Berkeley Preliminary Exams. Well, you can find problems from real analysis, differential equations, number theory, abstract algebra, linear algebra, and so on. And one of the problems, it's the following one. And I've noticed the fact that they like to collect some old Putnam problems and put them at the qualifying exams. Anyway, it's Berkeley. For which constant C, for which real number, let's say, C is the following inequality. Let's write it in this way: e to the x plus e to the negative x, everything, so the arithmetic mean of these two numbers is less than e to the power c times x for all real x. So we would like to find the let's say the least constant c for which this happens, right? All right. Well, when you see this kind of problem, well, you will be tempted to take the derivative of that. Maybe you can, yeah, you can do that as well. But yeah, I think this is how it was done in the Berkeley book. I don't recall exactly their solutions, but anyway. Well, when you have e to the x, there is also another idea to consider. Maybe you can write this as a Taylor series expansion of e to the x. So we use the Taylor series expansion of e to the x. And for, let's take the constant c greater than 1/2, and you will see why. So I have a hunch that this would be the constant. We have that, and I'm going to write it in this way: e to the x plus e to the negative x, everything over 2, right? This would be, and now I'm going to expand in Taylor series, both of them, right? And once I expand, all the odd terms will just vanish, right? So it will, we will have only so we will have the sum from n equals 0 to infinity of x to the 2n. So we'll have only the even ones, right? Okay. And this will be less or equal. And also, I'd like to compare with the Taylor series expansion of e to the power 1/2 x squared. So this would be less than, and here I'm going to use an inequality which, well, follows immediately even by an induction, but you can use Stirling's approximation theorem. But anyway, let me just write it. So it's 2 to the n times n factorial, which is nothing else than e to the 1/2 x squared. Well, and this is less than this guy. Since, and here, where we used the inequality, and here we use the following inequality: 2n factorial is greater than 2 to the n times n factorial. Anyway, that's pretty easy to see. I'll leave it for all n greater or equal than 1. And I'll leave this to you as an exercise. You can prove it by induction, you can prove it just by computations and so on. All right, so we have seen the fact that for c greater than 1/2, we have this inequality here, which is great. All right. And now let's see the other way around. So conversely, if the inequality holds, we would like to show that that c is 1/2. If the inequality holds for all x, for all real x, right? Then I'm going to do the following. And here I'm going to take the difference between the two, and I know that 0 is less than, and I'm going to take the limit as x approaches 0 of e to the power c times x squared minus 1/2 e to the x plus e to the negative x, everything over x squared. And this guy here will be, if we expand this, so we use again the Taylor series expansion, so let me write it here. So if we use the Taylor series expansion, we will have the following. And now let's be careful here. So we will have that this guy is, so here I have x squared, and here in the first parentheses, I'll have 1 plus cx squared plus so on. And here I'll have minus 1 plus 1/2 x squared plus so on, right? And this guy, by if you look, this is nothing else than just, guess what is what? C minus 1/2, right? Yeah, C minus 1/2. Right, it's pretty obvious. You can do L'Hopital if you want, whatever, but you can just take the coefficient of x squared. All right, you see on the top is c minus 1/2, and on the bottom is 1. So this is c minus 1/2. So this implies that so c is greater than 1/2, and that's it. See? So the conclusion follows. All right. Right, so that was the trick. Well, I wanted to do this problem. It's pretty easy, I would say, as long as you know what to do. It's just by the main idea is just to use the Taylor series expansion of the exponential. Anyway, in the same spirit, I'd like to do the following problem. Again, this was a Putnam problem. So problem 4 was a Putnam. And you will see that I will use a very, very similar idea. So it was a Putnam B3 in 2002. And the problem says the following. Show that for all integers n greater than 1, we have the inequality 1/2 to n times e is less than 1/e minus 1 minus 1/n to the power n, less than 1/n times e. All right, so this is the inequality. Keep in mind that this number e, so let me recall that e is defined by this limit. So the limit as n approaches infinity of 1 plus 1/n, everything to the power n. So if you look at this, it's kind of it's a very nice inequality, because if you multiply it by e, right, or by n, for example, you can obtain something about this. The first error term from the asymptotics of 1 minus 1/n to the power n. Anyway, we'll make this comment at the end. So how should we prove this kind of problems? Well, the thing is that also you can maybe you can use some ideas regarding the proof of the monotonicity of this Euler sequence. So this is what we call Euler. This Euler's sequence. Sometimes we call this E, so this is this sequence here, and is En. Right, I already talked about this when we dealt with sequences of real numbers, right? Okay. So maybe, well, I haven't planned here to use something similar as in the previous problem. Maybe we use the Taylor series expansion, but this time not of the exponential of the but of the logarithm. The Taylor series expansion of log of 1 plus x. So this would be nothing else. We can write this in the following way. You know that is the Taylor series expansion is of this form for x an absolute value less than 1, right? Or equivalently, we would like to use it in the following form. Equivalently, log of 1 minus x is the sum of n equals 1 to infinity of x to the n over n, right? Again, for x less than 1. All right. Now we're gonna, so our inequality will be by taking the logarithm, right? It will be equivalent with the following fact. So by taking the logarithms, our inequality is equivalent with the following. So let's see. So I don't know. So let me write it in this way. 1 minus 1 over n is less than the exponential of okay, 1 plus n log of 1 minus 1 over n, and this will be less than 1 minus 1 over 2n. So that's the inequality that we have to prove, right? Anyway, this is just the same inequality by taking the log, right? Look at them, both of them are here. See, they're equivalent. So maybe we will prove this last one. And now at this point, well, we can write this in, this will be equivalent. We can write this a bit by taking the log here. This would be log of 1 minus 1 over n less than 1 plus n log of 1 minus 1 over n less than log of 1 minus 2n. And in fact, we will prove this last one. This is the one that we would like to prove. So if we prove this one, we proved our conclusion. And now, as you can see, I have this log here, the log of 1 minus 1 over n and log of 1 minus 1 log of 1 minus 1 over 2n. So maybe we could use, so we know that from the Taylor series expansion of the log, we know that negative, let's write it of log of 1 minus x is negative this sum for x less than 1. So the above inequality, so the last inequality is equivalent with so this will be equivalent with the following. Let's write it. So this will be, the first one will be the sum from I, let's say, equals 1 to infinity of 1 over I times 2 to the I times n to the I will be less than the sum from 1 over I plus 1 times n to the I And the last one will be the sum I equals 1 to infinity of 1 over I times n to the I. Well, this last one, well, I would say both of them are equal, which is trivial because, well, the second one and the last one is quite clear because I plus 1 is greater than I. But the first one and the second one, well, because 2 to the I is greater or equal than I plus 1. For all I greater or equal than 1. You can prove this by induction or using Bernoulli's inequality, whatever you want to do. And that's it. And that's the end of the problem. All right, so this was a nice problem. As you can see, you only use this fact in this form. Look here. Right? But now I would like to point out a remark. And let's go back to our initial problem. Well, let's multiply by n. And, well, unfortunately, what I would like to point out is that this inequality is not sharp enough to give us, so if we multiply by n, so the inequality can be restated as okay, let me restate it as 1 over 2e less than n times 1 over e minus 1 over n to the power n less than 1 over e. And as you can see, if I take the limit as n approaches infinity of that, it won't give me the exact limit. So if I want to apply the squeeze theorem, it doesn't work. So unfortunately, the above inequality will not give us any information about this limit, about the limit as n approaches infinity of n times 1 over e minus 1 over n to the power n. Doesn't give us any. Anyway, maybe we should use some different method to prove this. All right, I think I'm going to stop here for today. Next week I will start something new. We will be talking about integrability. We will talk about well, Riemann sums and some other techniques involving integrals. And then at some point I will connect this with some differential equations. And then at the end, at the very end, I will do some multivariable calculus. All right, I'll stop here. Thank you very much.